I'll start with module 2. Module 2, that is FET and SCR. Okay, this will be there for your second internals. Okay, along with the topics which we have covered yesterday. Okay, so FET is one portion and SCR is another portion in this module. So if I want to start with FET, what is FET? If I abbreviate it, it is field effect transistor. So probably the transistor term itself is new to you for many people, because in your syllabus they have directly started with FETs before starting transistors. Okay, actually they should have started with transistors and then FETs should have come the later part. Okay, anyhow, it is also similar way of understanding. If you see the specifications of this FET, okay, what are the things that will be noticing is these FETs are, okay, it is a 3-terminal device. Okay, it is a 3-terminal device. FETs are 3-terminal device like diode. So if you see the diode structure, it is this, right? So you have anode and cathode. It is a 2-terminal, means you have 2 terminals for this, right? So like in the same way, FET has 3 terminals. Okay, so which are those terminals is, say if this is an FET, so FET, so it has 3 terminals. Okay, so one is gate. Okay, next is drain, we term it as D, gate we term it as G, and the other terminal is source, we term it as S. So this is drain, source and gate. So it is a 3-terminal device. Okay, and it is unipolar device. Unipolar device. What is meant by unipolar? That is only one type of charges will be responsible for current conduction. Okay, so that is called unipolar. Unipolar means single type. Okay, single type of charge carriers, that is either electrons or holes, will be responsible for conduction of current. If you take a transistor, that is, it is a transistor is actually a BJT, we say it as. Okay, generally this BJTs, in BJTs it is called as bipolar devices. Why it is called as bipolar devices? Because both electrons and holes will be responsible for current conduction in case of transistors, that is BJTs. Whereas in FETs, only one type of charge carriers will be responsible for current conduction. That's why it is called as unipolar device. Okay. Next, if you see the size of this device, okay, if you compare the size of this device with transistors, okay, the size of this device will be small size. Okay, the size is small compared to transistors. Okay, compared to transistors, the size is small compared to transistors. Okay, that's why it is widely used in ICs, widely used in IC technologies, because the size is small. That's why it is widely used in IC technologies. In integrated circuits, this FETs are used. Okay, these are the few introduction about FET. Okay, the FET is termed as field effect transistor. It is a three-terminal device. The three terminals are gate, drain, and source, and it is a unipolar device. That means only one type of charge carriers, that is either holes or electrons, will be responsible for current conduction in the circuit, and the size of this device is small compared to transistor. Okay, these are the few things that you should keep in your mind when FET comes into picture. Okay, now we'll see the classification of this FETs. Okay, FET classification. Okay, so FETs are mainly classified into two types. It is mainly classified into two types. First one is JFET. J refers for junction field effect transistor. Okay, junction field effect transistor. Okay, and MOSFET. MOSFET. What does this mean? Metal oxide semiconductor field effect transistor. Okay, metal oxide semiconductor field effect transistor. Okay, this is the abbreviation of these two terms, that is JFET and MOSFET. Okay, FETs are broadly classified into two types, JFET and MOSFET. Again, this JFET is classified into two types. Okay, N channel, N channel and P channel, N type and P type. Okay, NJFET and PJFET. You can JFET and PJFET. Okay, N channel junction field effect transistor and P channel junction field effect transistor. And if you come to this side, it is classified again into two types. Okay, that is depletion and enhancement. Depletion and enhancement. Okay, again this depletion is classified into two types, N channel and P channel. This enhancement is classified into two types, N channel and P channel. Okay, so you can term this as N channel depletion type MOSFET, P channel depletion type MOSFET, N channel enhancement type MOSFET, P channel enhancement type MOSFET. So totally there are six types of FETs. One is N channel JFET, P channel JFET, N channel depletion MOSFET, P channel depletion type MOSFET, and N channel enhancement type MOSFET and P channel enhancement type MOSFET. So totally there are six types of FETs that we are going to study in this module. So this completes FET part, that is first portion. Okay, so now we'll start with JFET. Any doubt till here?
No, sir.
Right. We'll move on to JFET because that is the first part which we are going to study. We are going to complete first this and then we are going to move for MOSFET. Okay. So if you see JFET, so I'll start with construction. Construction of JFET. Okay. So in JFET you have two types, correct? So that is N channel and P channel. So what I'll do, I'll take out some document PDF. In this I can show you clearly. Okay, so that I can move fast. Okay. So in this diagram you can see the construction or structure of JFET. Okay, I told you there are two types of JFETs. Okay, this is N channel JFET. This is N channel JFET, and The bottom one is P channel JFET. This is P channel JFET. Okay. So if you see the structure, how this structure is formed, let us see that. Please understand this very clearly so that if you understand this, rest all five will be easy for you to understand. Okay. See, you have a N type semiconductor. Can you see this? This is N type semiconductor. Okay. Upon this is this rectangle box. Okay. Full. Okay. Upon this N type semiconductor, they have diffused a P type heavily doped semiconductor. This one. Okay. On both sides of this N type semiconductor. Okay. They have diffused this P type semiconductor. Okay. So they have diffused this p-type semiconductor upon this n-type semiconductor. This n-type semiconductor is lightly doped compared to this p-type semiconductor. Okay. So once this is done, the p-type semiconductors both sides, that is this and this, are internally connected. Can you see? It is internally connected. Okay. This won't be visible to you. In the manufacturer side itself, they will be connected inside. Okay. So no need to write this in your exam, or if you want to write, you can show it as it is. So it is internally connected, means it is shorted internally, and a terminal is taken out at one p type. So this is a terminal. Okay. And is taken out one type, and that terminal we represent it as gate. The terminal we represent it as gate, and other two terminals are taken out at the two ends of the channel. That is, this is the n-type semiconductor. Okay. So the charge particles will move from source to destination, source to drain. From this source, this is the source, right? From source to drain, the charge carriers should move. Okay. So this is the channel, means the road or the path on which the charge particles moves is called as channel. So in this case, it is n channel, because the majority charge carriers here are electrons. Okay. The majority charge carriers here are electrons. So at the top of this n-type semiconductor, lead is taken out and it is termed as drain. Okay. It is termed as drain. At the bottom, one more lead is taken out, one more contact is taken out, and it is termed as source. Okay. So this is the construction of this JFET, n channel JFET. Why it is called as n channel? Because the channel is of n medium. Can you see? The channel is of n medium. Okay. N-type semiconductor. That's why it is called as n channel JFET. Okay. So if you just want to look at p channel JFET, you can see the bottom one. It is almost similar, except, as I said, the channel should be p type. So p channel means the channel should be p. That's why the first material will be p. Okay. P type semiconductor. Upon p type semiconductor, a heavily doped n type semiconductor is diffused. Okay. At the two sides, and it is shorted and forms a gate. The n type semiconductor is shorted and it forms a gate, and the p type at top, it is drain, and n type at the bottom contact is called as source. Can you differentiate the n channel and p channel JFET structure? Are you able to differentiate now?
Yes, sir.
Right. So this is the construction of n channel and p channel JFET. Okay. So now this is the symbol for n channel, and this is the symbol for p channel. This is the symbol for n channel, and this is the symbol for p channel. You can see that the arrow mark is inside here. Okay. For n channel, and here the arrow mark is outside. That's the only difference. Okay. So for p channel, the arrow mark is outward, and for the n channel, the arrow mark is inward. Okay. So this is the small difference in the construction of JFETs for n channel and p channel. Okay. Now we will see the working of this n channel and p channel. Okay. In order to understand the working, okay, first we need to understand the biasing concepts. Okay. So in order to understand the working, we need to understand the biasing first. Okay, how to understand the biasing? You follow me very carefully. If you have any doubt, you ask me then and there itself, because this concept, if you understand, the same concept will be there for all the FETs. Okay, see, this structure you know now, correct? The structure of JFET you know now, correct? So the working can be made understand in two steps. Okay, so first case is, case one is, I'll write here itself. Case one is no, not applied VGS comma R and VDS is applied in steps. I'll make you understand what is this. Okay, this is case one. Okay, case one. Okay, so if I want to elaborate this, what is this? So you can refer this diagram. Okay, this is for case one, no bias voltage on gates. Can you see this? This is what it is. Okay, so I'll just zoom it. Right, see, it can sometimes you see the channel is N, this is N type material, correct? This is N type material first. Okay, so very simple in understanding this concept. It will be there for you forever to understand in any further understandings of FETs. See, if I want to, what are the majority charge carriers in this N region? What are the majority charge carriers in this N region? Can anybody tell? Yes? Please someone respond. What are the majority charge carriers in N-type semiconductor?
Electrons.
Yes. So there are majority charge carriers as electrons, correct? In N-type semiconductor. Okay? So these are the majority charge carriers, and holes are very small. That is, minority charge carriers of holes will be there here and there. Now, always remember how to bias this, the concept I'll teach you now. Okay, see, always remember the majority charge carriers which are there in this channel, whether N channel or P channel. Now we are looking in N channel. So in N channel, what are the majority charge carriers? It is electrons. This electron should be pulled out to the potential here. Did you understand what I'm saying? The majority charge carriers in the channel, in this case it is N channel, that's why the majority charge carriers are electrons. This electrons should be pulled out to the potential here. So what type of biasing I have to give here? So it should be plus, correct? Am I right? Yes? Am I right? The majority charge carriers are holes, I mean electrons in case of N-type semiconductor. That's why the VDS, hello? Yes, sorry, there was a call. Okay. So the majority charge carriers in channel here is the electrons, because it is n channel. So this electrons, the majority charge carriers should be pulled to this potential. So that means this potential should attract the majority charge carriers which is there in this channel. So what type of polarity that I have to give? I should give positive, correct? That's why
Yes,
it is
sir.
positive. Yes. So I'll term this as VDS. Very simple. This is how you are going to define this VDS. Did you understand how I am defining the VDS? The same concept will be used for all the circuits, all the 6 circuits. So you should remember this, how I have defined this VDS. Okay. Now, so this is first step. Okay. And if you see what I have written here, not applied VGS means I am not applying gate voltage, means VGS is 0, that's why it is shorted. Can you see? Gate to source is shorted, means I am not applying VGS. Okay, for case 1. Okay, that's what here they have told, no bias voltage on gate. Okay, that is figure A. Okay, so now for this, what we have to do, VGS is fixed at 0, and VDS you are varying in steps. Okay, so this is variable in steps. That means I am varying this from 0 to 25 volts. Okay, now for this, how does the VI characteristics looks like? Let us see that. Okay, now if you see the VI characteristics of this, okay, it looks in this way. Okay, this is the VI characteristics of N channel JFET. So this is VDS. This graph is x axis is VDS. Can you see here? This is VDS. It is positive. That means it should be in first quadrant. Correct? Can you see? Why it is positive? You have seen there. See here. VDS is positive because plus and minus, plus is at the top and minus is at the bottom. That means it is positive. That's why your VDS is in x-axis, positive side, that is first quadrant. Okay, and where is current? Current is in the y-axis. Okay, so if I want to draw the VI characteristics, initially anyhow VGS is 0. Because of this 0, there will be small depletion layer formed between this P and N junction. That is what this is, depletion layer. Okay, this region is depletion layer. Okay, you can notice there at the both the sides. Okay, so that means because of this 0 volts. Okay, now I'll give 0 VDS. That is the first step, because I am varying from 0 to 25. I'll start with 0 volts. For 0 volts, this is the first step. Okay, for 0 volts, this VDS won't attract any electrons from this. Correct? This VDS won't attract any electrons. That's why the output is 0. That means that the ID is 0. That's next. I'll increase VDS to second step. I'll increase VDS to 1 volt. If I increase to 1 volt, what happens? Small pull will be there from this VDS for this electrons. That means, say for example, there are 1000 electrons in the channel. Just an example, there will be millions of electrons. Okay, just for your understanding, I'll take there are 1000 electrons in this N channel. Okay, because of application of this 1 volt from VDS, so out of 1000 electrons, so okay, say for example, 200 electrons will start moving in the circuit. This VDS will be able to attract just 200 electrons out of 1000 electrons because of this 1 volt. Okay, so what happens if you look at the graph? Okay, that is one step. Okay, next I'll increase this to 2 volts. This VDS I'll increase it to 2 volts. What happens? For 2 volts, this VDS is able to attract nearly 400 electrons. Okay, next I'll increase this to 3 volts. So almost 700 electrons will take part in movement. Okay, next I'll increase it to that fifth step, I'll increase it to 4 volts. All 1000 electrons will take part in movement. Now if I increase at the sixth position to 5 volts, what happens? No more electrons are there, so it remains at 1000 electrons only. That means it is becoming constant here afterwards. If you increase whatever voltage VDS, that for all 1000 electrons which are there here are taking part in the circuit conduction. Okay, so that's why if you see the graph, okay, if you see the graph for this, for VGS is equal to 0 and VDS varied in steps. If you see the graph for this, it looks like this. Can you see here? See here, VGS is equal to 0 means for 1 volt there is few electrons, for 2 volts there is few more electrons, for 3 volts it is increasing. Okay, it is as you increase VDS, okay, the current is also rising slowly. Okay, it is rising. At one point it becomes constant. So the electrons, all 1000 electrons will take part in movement. No further increase in current. Okay, so it becomes constant. Understood? This is for VGS is equal to 0 volt. Okay, this is for VGS is equal to 0 volt. Now what you need to understand is the current will increase linearly to a certain voltage and then it becomes constant. So the point where the current becomes constant, that point is called, if you draw a line of that, this point is called as VP, pinch off voltage, for VGS is equal to 0. Okay, understood this graph how we got for VGS is equal to 0? Any doubt in this? Yes, have you understood this graph how we got?
Yes, sir.
Right. So this is for VGS is equal to 0. Next we will move on to for VGS is equal to minus 1 volt. So if you see, this is here VGS is 0, that's why it is short circuited. Now if you see the B diagram or B figure, now I am applying VGS, that is 1 volt. Okay, I am applying VGS as 1 volt. So it is negative volt because it starts from negative battery, negative terminal. So it is minus 1 volt. Okay, so if I apply minus 1 volt, what happens? Can you see? P type is connected to negative terminal. It is reverse biased. This is what you have to do. Always VGS should be reverse biased. Keep this in mind. Okay, so if it is reverse biased, means positive terminal is connected to negative polarity of the battery and negative terminal n type semiconductor is connected to positive terminal of the battery. That means this is reverse biased. This is reverse biased. Okay, so because of this reverse bias, what happens? Okay, what happens? The depletion layer between this P and N channel, what happens? Because of reverse bias, what happens to the depletion layer? It will increase. Can you see here? It was very small. Now it has increased. Can you see? It is increased. Okay. Similarly, here also it is increased because these two are short circuited internally. Okay. It is increased at both the sides. The depletion layer encroached into the channel. Okay, it means it has encroached into the channel. Okay, what does this mean? What happens to the channel size now in this case? Because of this negative voltage applied on VGS, what happens to the channel size now? Yes, what happens to the channel size? Depletion layer increased or encroached into the channel. Because of this encroachment, the channel size decreases, correct? Did you understand this?
Yes, sir.
So if the channel size decreases, in the first case there were 1000 electrons, just an example. But in this case, there will be just 700 electrons totally, because the channel size decreased here. Understood? So the total number of electrons reduces in the channel. The majority charge carriers reduces in the channel because of this encroachment of this depletion layer, because of this negative biasing. Okay, reverse biasing. Okay, what happens now? You vary VDS slowly in steps as we did here. Okay, so for it follows the same procedure. What happens here is, this case 2, can you see? You will get the same graph, increase VDS in steps. Okay, it will the current starts increasing slowly, increases slowly, and at one point it becomes constant. Okay, it becomes constant. This is for VGS is equal to minus 1 volt. Why it is less compared to here? Why the saturation is less for VGS is equal to minus 1 volt? Because here we had 1000 electrons, that means all 1000 electrons are taking part in electron movement. That's why current will be more. Here only 800 electrons are there because channel size has decreased. That's why the current, saturation current also will fall down. Understood? Understood? Yes?
Yes,
If you
sir.
say yes, I'll move on to the third step. Any doubt here? How this saturation has come down? Because the channel size decreased. If the channel size decreased, the number of electrons in the channel also decreases. So number of electrons decreases means even the saturation also will fall down. That's why we will get lesser saturation for more negative voltage applied to the gate. Understood? Yes?
Yes, sir.
Right, thank you. So let us see the third step. That is, I am applying more negative voltage to the gate. Okay, I am applying more negative voltage to the gate. If I apply more negative voltage to the gate, that is, I'll apply now say 2 volts. Okay, I'll apply now 2 volts. It was 1 volt, again I'll apply for 2 volts. So what happens? It is more reverse biased between this P and with this N semiconductor. That's why the depletion layer further increases into the channel. Can you see? It is more into the channel again because of this more negative voltage applied to the gate. So what happens to the channel again? The channel size again decreases more. Okay, so what happens to the number of electrons? Again the number of electrons also will decrease. If you see the graph, okay, the as you increase the VDS, it will, the current slowly increases, but the number of electrons are reduced from 800 to say for example 400 because of reduced in channel size. So at the current becomes saturated at lesser current itself. Okay, so this is what for VGS is equal to minus 2 volts. Again if you further increase, again the saturation will fall down. Okay, so at one point what happens? Okay, so this channel, okay, this encroachment of this depletion layer is completely blocked in the channel. Can you see here? The encroachment is completely blocked. There is no space for electrons to move from source to destination, source to drain. Means whatever the conduction is happening here, it's like, if the electrons are moving from in this direction, correct, electrons are moving from the drain towards this direction, that means in which direction current will get? If electrons are in this direction, obviously the current will be in opposite direction. This is the direction of current, so this is ID, correct? Opposite direction of electron movement will be current, correct? So uh, the current will, means the electrons are moving in this direction. Okay, it completes the path, it moves, it circulates in the circuit, it keeps on circulating like this. Okay, that's how the current will keep on flowing. Similarly here, the current will, electrons will start circulating like this and come to the source and move in this path. Okay, similarly here what happens? Because of more negative bias, there is no path for the electrons to move from source to, it will block here because of this depletion layer encroachment. Okay, it can't move from source to this drain. Because of this complete blockage of this channel, the current can't conduct further. This is what it happens finally. Can you see here? So for more VGS, the current will stop conducting further. Okay, this is all about VA characteristics of N channel JFET. Understood? Any doubt in this?
No, sir.
Right, good. So in this, what if they ask you to explain the regions of operation of N channel JFET? Okay, what you need to answer is there are 4 regions totally. Can you see? This is ohmic region. Okay, there is one region called ohmic region. Okay, and we have something called pinch off region. Okay, and we have something called breakdown region, and we have something called pinch off voltage. Okay, so 4 points you need to explain. One is ohmic region. Second one is saturation, or you write it as pinch off voltage. Third one is saturation region or pinch off region, we say it as, or pinch off region. That's what they have told here. Fourth one is breakdown region. Okay, so these 4 terms you need to explain. What is ohmic region? You can see here. So from here to here, the current increases with voltage applied. That means it is in resistance. What is resistance? R is equal to V by I. So means as current increases, voltage also increases. That's what it is. Okay, so this is ohmic region, means resistance region. Okay, so from here to here, it is as voltage increases, current also increases linearly. That's why this region is called as ohmic region. Okay, the circuit behaves perfect resistor in this region. Next, what is pinch off voltage? For VGS is equal to 0, the point from where the current becomes saturation, that point, what is the voltage? That voltage we say it as pinch off voltage. Okay, the voltage we say it as pinch off voltage. From that voltage onwards, the current becomes constant. The current goes to saturation. So that is called pinch off voltage. Okay, next is saturation region or pinch off region, means the current from the point where it is constant, from this point to this point, it is from point A to point B, the current is saturated, means it is constant. This region we say it as saturation region. Next, what is breakdown region? If you further increase the voltage VDS, okay, if you further increase the voltage VDS, what happens? Avalanche breakdown happens, means the device will start breaking down, means the current will start shooting up rapidly, and from where the device might get damaged. That is called as breakdown region. So these 4 regions you need to explain. Any doubt in this? Right, so this is for N channel. Okay, if you see P channel, okay, if you see P channel, how does it look like? Have you understood this N channel completely? Any doubt in this?
No, sir.
Right, good. So if you see P channel, how does the circuit look like? Can anyone guess? Okay, I am looking for the figure of that. Right, it is not here. Okay, anyhow, we'll draw that. So I'll just draw here. You need to analyze whether. So for P channel, the channel looks like this. Means for P channel means the channel should be of P type. The channel should be of P type. Okay. So in this P type, okay, this is P type. In this P type, I am doping N type semiconductor. Correct? This is N type semiconductor, and this is internally connected. These N types are internally connected to form a gate. And this p-type semiconductor at top and bottom are taken out as contacts to form drain and source, correct? So what are the majority charge carrier, how to bias this? Now you need to tell me how to bias this for p channel. What are the majority charge carriers in p channel? P-type semiconductor. What are the majority charge carriers in p-type semiconductor?
Holes.
Holes. So there are holes. Okay. So majority charge carriers are holes in case of p-type semiconductor. Okay. So these holes has to be attracted towards the potential which I am applying here. Correct. So what type of biasing I have to give here now? The holes should attract towards this terminal. What type of terminal I have to give here? Negative? Correct?
Negative.
Yes. So this I'll term it as VDS. Okay. So now holes are moving in this direction. So that means current also will be in the same direction as holes, that is ID. So current direction now it is in this direction. In case of N channel, the current was in opposite direction because electrons are moving in this direction. So current will be in opposite to electron movement. Whereas here the holes are moving in this direction. That's why the current also will be in the same direction as holes. Understood? So this is biasing. So case 1, same steps, means I am not applying gate, I am increasing VDS in steps. So VDS now it is negative, correct? So I will start from 0 to minus 25 volts. Why minus 25? Because VDS is negative now. Understood? VDS is negative in this case for P channel. Understood? Yes? This is case 1. So if you see the graph for this VDS, how does it look? If they have written, yes, they have written. See, can you see? VDS is negative. VA characteristics, VDS is negative. So it is in second, which quadrant is this? It is in second quadrant. Okay. So VDS is negative. You will start increasing VDS in steps. So VGS is 0. That is the case 1. So as you increase VDS in steps, the current also starts increasing linearly, and at one point it becomes constant. This becomes constant. This is for VDS. VGS is equal to 0. This is for VGS is equal to 0. Okay. Next, what is case 2? Case 2 is I need to reverse bias this gate and source. If I want to reverse bias, what happens? What type of biasing I have to give here in order to reverse bias? Can you tell? N2 positive terminal, correct? This becomes reverse bias. This is VGS, correct? So VGS now it is positive. That's why in the graph you can see, okay? So VGS now I will give as 1 volt, then 2 volt, later 3 volt. So first for 1 volt, I will see the graph. How does it look? Can you see here? For 1 volt, so it will increase linearly, okay, and it becomes constant at lower saturation. Why lower saturation? The same concept. What happens? Because of this 1 volt, okay, because of this application of this one negative voltage or reverse biasing, what happens? The depletion layer will encroach into the channel. The depletion layer will encroach into the channel. So because of this encroachment, what happens? What happens? The channel size decreases. If the channel size decreases, number of holes also decreases in the channel. If the number of holes decreases, obviously the saturation will fall down. That's what it has happened here. The saturation has fallen down. Similarly, for VGS is equal to minus 2 volts, again the saturation will fall down. Similarly, for VGS is equal to minus 3 volt, further saturation will fall down. Finally, it won't conduct. The same just opposite of n channel. This works, but it is n channel is in first quadrant. This will be in second quadrant. Okay, this is the difference between n channel and p channel working. Any doubt in this? Any doubt? Shall we move on to next topic, or we'll close the class here? I think it is already 11:51. Yes, I can wind up the class right now here. If you have any doubt, you can ask me in the next class. Okay. I'll just wind up the class here. Okay.